Hi everyone. Today we're going to be visualizing span and basically understanding if a vector is contained within a span of S. So how we do this is let's say we have a subspace of vectors, and the subspace elements are comprised of U and V. So it's a two-element subspace. U being 1, 2, -1. And v equals 6, 4, and 2. We would say that the span contains all linear combinations of these two vectors here. So the span of S contains every combination of u and v added and subtracted together. So let's say I did 2u plus 3v, or 2u minus 2v. Wherever those vectors are going to show up are contained within the span of S. And to visualize this, I have a little Desmos graph for you. And the way that we can describe the span of two non-collinear vectors is to draw a plane. Now, to do this, you would take the cross product of these two vectors, which you'd find to be some vector maybe pointing out this way. And then you could define the plane that way, which you'd find to be this. So every vector can be contained within this plane, and this is a way that we visualize the span of the subspace. And just to prove it, if I take some combination, let's say I take 2 of this first vector, then maybe I subtract it by this vector. See how it's still contained within the plane? So yeah. Okay, so how can we find this mathematically? Because it's very easy visually. The question that we're asking is this other vector w in the span of S? And that might be a little hard to prove unless you know the algorithm. Basically, if the vector w is in the span of S, the subspace S, then w must be in the plane somewhere. And let's see if that's the case. So let's put in, I'm going to make this vector blue. So if I make the vector blue, let's see, the vector that we're trying to prove is in the span. It is 9, 2, 7. And hopefully you can see that indeed this vector is in the span. But how do we prove it mathematically? Now, this is visual proof, but what's the mathematical proof? That's what I want to show you today. Okay, so to show that w is in the span of the subspace S, you have to prove the following relationship to be true. We know that if we add and subtract u and v in some proportion, we'll get w out because it's in the plane. We know that to be true already. So what must be true is that w, the vector w, must equal some linear combination of u and v. And to show this, we're going to define a variable k1 and u, and then we're going to add it to v with another coefficient k2. So we could imagine maybe we need to go out positive in the u direction, so k could be positive, but k2 could then be maybe negative, where we go backwards to recorrect and get to w. So it's just basic vector addition and subtraction if you think about it. But maybe this isn't a whole number ratio that's very nice. In our case, we'll find it to be a very nice number, but it might not be. It could be like maybe 1.3 times u, and then plus k2 being like, I don't know, 2.6, negative 2.6, and that corrects you to w, showing that it is in the span. Okay, so let's show this here. We know w is the vector 9 with component x 9, y component 2, and z component 7. And we know that this needs to equal a scalar multiple of u, which in our case is 1, 2, -1. Okay, so 1, 2, -1. And then we're going to add this to k2, which in this case is 6, 4, and 2. I'll leave it to you to add these together, but hopefully you'll find that this vector 9, 2, 7, w must be equal to the x component of the combined vectors being k1. So I'll show you how to do the x component. K1 multiplied by 1, and then we add it to k2 times 6 as the other x component. So this simply becomes k2. Okay, and then just do the same for the other components. For k2. And then for the z component, negative k1 plus k2. Okay, so basically what this is saying is that this vector can be described, if it's in the span of the vectors, as some combination of coefficients of these other vectors. So how do we solve for k1 and k2? Well, it's actually quite simple, although it's just a little tricky to see at first. Set each component equal to each other. So we're going to set 9 equal to the x component of our condition, 2 to the, and I'll color code this here, our y component to the y component of this like conditional matrix, or sorry, conditional component, and then 7 to its z conditional component. Now that's not really terminology that we use, but I think it's the best descriptor. So we're basically matching these, and we can actually put it in a matrix. I think it's important that I at least show you the system. I know it's going to take some time to write it out, but I think it's helpful. 9 equals k1 plus 6k2. You can skip ahead if, this is obvious to you, but for some people it's not so obvious, and I really want to make sure I don't lose anyone here. So 2k1 plus 4k2. And hopefully you can begin to see that we're getting a linear system out of this. A system of linear equations, I should say. This should be 2k2, I think. Yeah, this should be a 2 here. Sorry. 2k2. I'll just fix that there. 2. Okay, so now we can go ahead and put this into a matrix and solve for the coefficients. So 1, 6. See, I didn't want to jump ahead too far here in case I might lose anyone at. When you pull the matrix up, it sometimes you ask yourself, where do these numbers come from? Well, they come from this here. All right. And if you do some Gauss elimination, you'll find, at least I found, the matrix of 1, 6, 9. I left the top unchanged, but it is some Gauss elimination, and I found a really nice elimination to be this, which means that k1 equals negative 3, whereas k2 equals 2. So that means that what we need to do is to get W, one such linear combination could be k1, put a coefficient of negative 3, so negative 3 times of u, so go back u 3 times, and then add to that 2 of v. So let's go ahead and see if this holds. So here's our combination. So what I'm going to do here is just add each vector slowly, and then we'll superimpose them on each other. So our first vector is going to be negative 3 times. So you can see it kind of shoots out the reverse way, and we're going to make these vectors purple. And then for vector v, remember we said that I believe it's just 2 times. I'm going to double check myself here. Yeah, so it's 2 times, sorry. So you can see the two kind of shoot out in different ways, and let me make them both purple. So, and in between, if we were to add them together, their components going in opposite directions are going to cancel. and they're kind of going to mitigate to the purple or to the blue. So let's see if we get out our W vector and we add the two. So if we do the vector addition, we do in fact, and I'm going to make this orange, the vector addition, adding, and hopefully you can see that on the thing here. We're going to get out our vector that we wanted, the blue one, which is, we were asked, is it in the span? And that's the mathematical way to prove it. Because a solution exists to the linear system, the vector is in the span. Now, you could also do this for a vector that's not in the span. And in fact, you would find a contradictory statement in your elimination. You wouldn't find variables for K1 and K2. They just would not exist as possibilities, right? You know, it's just impossible. You can't. So, for example, if I had one that was like, I'll make some vector up right now. Hopefully it's not in the span. Let's just say -6. So maybe something that looks like a normal, almost, kind of a normal, not quite. But you know, this little gray vector, if we're looking at this gray vector, we ask ourselves, is there any combination of purple vectors here that could give us, or sorry, of the red vectors, sorry, not purple. Let me just get rid of all the junk. Is there any combination of the red vectors that could give us the gray vector? And the answer to that is no. There's no possible way, because it's just not in the span of the plane. All linear combinations is described by this subset of... So the whole 3D realm, R3, that is the vector space itself. But the vector space only has two elements, which defines the subspace of this plane, and the vectors contained on this plane cannot possibly make this vector in R3 that's not in our subspace. So I know a lot of lingo, but that's just kind of how you want to think about this. But anywho, guys, that is how you find if a vector is in the span. So thank you for watching. Have a good one. Bye-bye.